Hello everyone, this is your test for review. I'm going to go ahead and start with question number 1. A quality control expert at Glotech Computers wants to test their new monitors. The production manager claims they have a mean life of 85 months with a variance of 64. If the claim is true, what is the probability that the mean monitor life would be greater than 86.6 months in a sample of 122 monitors? Round your answer to 4 decimal places. Alright, so there's a lot of key information from this problem here. We're given that the mean is equal to 85. So you can call that mu, you can call that whatever you want. We're given a variance of 64, and we want to know the probability that it is greater than 86.6. Alright. And so we have a sample of 122. So what's the probability that that average is greater than 86.6? Well, to figure that out, we have to first figure out the z-score. And so the z-score, using the central limit theorem, z-score equals x minus mu divided by sigma over the square root of n. And that's because we're not just trying to figure out the probability that 1, we're trying to figure out the probability that the average of a group. So, and another key point is the greater than. So we have to use the right formula, of course. And then since the problem has greater than in it, that does mean something very important to us whenever we're trying to figure out the answer. So this in the denominator, that's your mu sub x bar. And this is directly related to the central limit theorem. And so we have to actually calculate that mu sub x bar. I said mu, I meant sigma, sorry, or sigma sub x bar. And so that's going to be the standard deviation divided by the square root of n. We have the variance. To find the variance, you take the square root, to find the standard deviation, you take the square root of the variance. So the square root of 64 is 8. That's pretty easy. Our mu sub x bar, that's the denominator for our z-score, is going to be equal to 8, that's this, divided by the square root of 122. Alright, Rn. And so I like to try to keep things exact as possible. I usually carry my decimal places out pretty far, even though, this is still an estimate. It's just a pretty close estimate. And so that's my mu sub x bar, and anytime I need to use that in any formula, I always plug in, 5, 6, 7 decimal places, so that whenever I go to round to 1 or 2 decimal places, I'm sure that I get the answer right. It's not good to plug rounded values into formulas, which I'm sure you already know. Alright, so our z is going to be equal to x, that's 86.6, minus mu, so minus 85, over mu sub x bar, which was that, so 0.724285968. So when I divide that, I need to round that to 2 decimal places. All z-scores rounded to 2 decimal places. That's going to be 2.21. Now, what that actually means, if we want to know the probability that we would have something greater than 86.6, if we were looking under the normal curve, you know, this is where we get all of our probabilities from, the area under this curve here. There is some z-score of 2.21 that's pretty far to the right. Remember, right here in the middle we have z equals 0. And so there's some z-score that's pretty far to the right that would be 2.21. If this problem would have said less than, then we would just take the value we would get from the table, the z-score table that's in the back of your ebook, of 2.21. But we want to know greater than, and since it's greater than, that means we want to know the area to the right. So we have to say 1 minus the value you get from the table. Okay? And so here's a link for tables here. Of course, you have to pull up the right table. You have a lot of different tables. Let's see. So we have lots of different tables too. It's kind of confusing that we have so many standard normal tables. So I usually just use the one out of the back of the book, to tell you the truth, because some of these in this program seem to be a little confusing. Like here's the negative z-score values. I mean, you can use that. That's not on your formula sheet, by the way. For some reason, if you look through your formula sheet, it'll say like table A, table B, table C, table D. Well, actually, I believe it's either B or C is missing. I don't know why they elected to do that. It is in the back of your book. It's around 796 or something like that. Yes, it is 796, and it's table B. That's the negative z-score chart. We don't need that one on this problem because we have a positive z-score. So we need the positive z-score chart. Okay, and so that wasn't the top chart. That wasn't the area 0 to z. That was infinity to z. Most of the time I use the tables area negative infinity to z and area negative infinity to negative z. I just use those. And so what I want to do is I want to look up the z-score that I had, and I want to say 1 minus whatever the area is for the z-score that I had. So I had a z-score of 2.21. So there's 2.2. 2.21 would be 0.9864. So I need to come here and say 1 minus 0.9864. And that gives me 0.0136. That's my probability. So what does that actually mean? I mean, you enter it in as a decimal in the problem, but that means there's a 1.36% chance that the actual mean would be greater than 86.6 for a group of 122. Okay? So, you know, your tables can be found by just clicking this button and then clicking on the right table. All right, number 2. And I'm not going to enter in the answers. I already know all these answers are right. I've already double checked them all. So previous tests I have entered them in. It just takes too long. All right, the mean cost of a 5-pound bag of shrimp is $46 with a variance of 64. If a sample of 53 bags of shrimp is randomly selected, what is the probability that the sample mean would be less than, that's very important, $43.9. Round your answer to 4 decimal places. So we know that the mean is 46, the variance is 64, the n, the sample, is 53. We want to know the probability that the mean is less than, very important, less than 43.9. Okay? And so in our formula, that's our x, or our x bar in our z formula. This is another central limit theorem problem because the n is not just 1, it's 53. We're taking 53 and wanting to know if the mean, the probability that the mean is less than 43.9. Okay? If a company knows the mean is supposed to be 46. Alright, so we need to calculate, so we have x bar minus mu over sigma sub x bar. So we have to calculate that sigma sub x bar. That's equal to n over, I'm sorry, not n, sigma over the square root of n. So that's going to be, the square root of 64 is 8. 2 problems in a row. And then the n was 53, so that's over the square root of 53. When you do that in a calculator, you should get 1.098884512. And so we can find the z-score by saying 43.9 minus 46 over 1.098884512. So subtract that, divide, and you will get a z-score of negative 1.91 when you round that. And again, remember, we round all z-scores to 2 places. Alright, so I need the negative z-score chart. But if you pull out your formula sheet, again, it's not there. So you do have to go to the back of the ebook to page 796, or in your test, you click on tables, go to standard normal table, and then we have area negative infinity to negative z. Now you got to be careful about how you read this table because it's a little different. You see, it doesn't start at 0, it starts at negative 3.4, and then the first column is the ninths. So that's negative 3.49 as a z-score at the top, and then we get smaller as we go to the right and down. So we're looking for negative 1.91. And remember, our problem was less than. Less than's a big deal because that means we can just take the value from the table. So negative 1.91 is on down. Negative 1.91. All right, I have 0.0281. Okay. 0.0281. That's my answer. Alright, the mean number of words per minute typed by a speed typist is 104 with a variance of 196. What is the probability that the sample mean will be greater than 104.7 words per minute if 100 speed typists are randomly selected? Round your answer to 4 decimal places. And again, on number 2, we take the answer from the table, so that answer was 0.0281. Right, so I'm going to write down the information. The mean was 104 on this one. This is the speed typist problem. The variance is 196. And let's see, the sample size is 100, and we want to know the probability that the mean is greater than 104.7. Greater than means we're going to say 1 minus whatever area we get for the z-score that we find. We were given the variance. The standard deviation is the square root of the variance, so it's going to be the square root of 196. I'm just going to leave it like that for now. The z-score is going to be 104.7 minus 104 divided by, now this is our sigma sub x bar. On all the other problems I've just been working it over to the side. How about I just put it down here? Sigma sub x bar is equal to sigma, that's the square root of 196, over the square root of n. That's the square root of 100. Well, that is 10, so you can write it as 10 if you want. Anyway, calculate this in your calculator and you should get 0.50. Alright, so we want to say 1 minus whatever area we get for 0.50. That gives us the area to the right since we want greater than. And so if you go to your table and you go to 0.50, we want to subtract 0.6915 right here. So that's 1 minus 0.6915. That's 0.3085. So what does that mean? That means there's a 30.85% chance that if we randomly select 100 speed typists, that their average would be greater than 104.7 words per minute. Number 4. Thompson & Thompson is a steel bolts manufacturing company. Their current steel bolts have a mean diameter of 133 millimeters and a standard deviation of 6. If a random sample of 43 steel bolts is selected, what is the probability that the sample mean will be greater than 132.4 millimeters? So greater than, that's important to this problem as well. That lets me know that I'm going to say 1 minus an area whenever I have to figure that out. So I was given that the mean of these bolts is 133. We're actually given standard deviation in this problem, not variance. We told standard deviation is 6. The random sample is of 43 of those, and the probability we are trying to figure out is if the mean would be greater than 132.4. Alright, so greater than, again, we're going to say 1 minus. We want to know the area to the right of whatever z-score we figure out. Okay, so our z-score is going to be equal to, it's 132.4 minus 133 all over, that's sigma over the square root of n. Remember, central limit theorem. If we have more than one we're choosing from, actually n is greater than or equal to 30, then we're going to do this. So we do sigma over the square root of n. So work all that out, and you should get, when you round to 2 places, negative 0.66. So we need that negative z-score chart, the one that's not in your formula sheets. It's on page 796 in the back of your ebook. Or you can look at it right here. This is the most convenient one, the one that says negative z on it. And then negative 0.66. So we have 0.25. Let's see. negative 0.6, 0.2546. All right, so 0.2546 is what I'm given. So 0.2546. And that gives me 0.7454. So that means there's a 74.54% chance that if you took a group of 43 of those, they would have a mean greater than 132.4. Number 5, the quality control manager at a computer manufacturing company believes that the mean life of a computer is 120 months with a standard deviation of 10. If he is correct, what is the probability that the mean of the sample of 90 computers would be less than 117.13 months? Round your answer to 4 decimal places. Okay. So basically the same type of problem. Mu equals 120. We were given standard deviation of 10. We want to know the probability that the mean would be less than 117.13, and we are given, if we took a sample of 90. So Z equals 117.13 minus 120 over, again this is sigma divided by the square root of n. And if you round that value, you should get negative 2.72. Now since this problem was less than, we're going to take the area from the actual table. And we're looking for negative 2.72. It's 0.0033. So the area is, or this thing right here is equals 0.0023. I said 23. Sorry, I meant 33. That's what was in the table, 33. All right, number 6. On these next couple, it's important, these are a little different, so it's important that we look at the less than or greater than as well. But these are kind of the same, yet just a little different. Suppose a batch of metal shafts produced in a manufacturing company has a variance of 6.25 and a mean diameter of 206 inches. If 90 shafts are sampled at random from the batch, what is the probability that the mean diameter of the sample shafts would differ from the population mean by less than 0.3 inches? So, what was the population mean? We were told the mean was 206. And we want to know that if you take 90 of those, what's the probability that all of them would be within 0.3 inches of 206. So it doesn't say 0.3 inches greater, or it says point will be less than 0.3 inches. Alright, so what is the probability that the mean diameter of the sample shafts would differ from the population mean by less than 0.3 inches? So that means it can be 0.3 inches bigger or 0.3 inches smaller. Okay? So even though it says less than, that still means 0.3 inches bigger and 0.3 inches smaller. You may need to read this problem a couple times to understand exactly what it's talking about. But what that's going to make us do is find two z-scores and get the area between the two, actually. So we were given less than 0.3 inches difference. And we were also given that the mean is equal to 206, that the variance is equal to 6.25, that random sample of 90 is what we were going to take. And so if 206 is the population, that's actually the population standard deviation, so that would be like mu, then we need to say mu minus 0.3 and mu plus 0.3, right? Because that will give us everything within 0.3 inches. So that would be, if we say 206 minus 0.3, we have 205.7. And if we say 206 plus 0.3, we have 206.3. So if we find a z-score for this one, a z-score for this one, so this is what we'll be finding. We'll be finding a z-score for less than, that'll be negative, a z-score for greater than, that'll be positive, and then we'll get the area between the two, and that's the probability that we would select one and it be 0.3 inches or less in difference of size. Okay? So this is still a central limit theorem problem because we're choosing 90 of these. So I'll say 205.7 minus 206 over 2.5 divided by the square root of 90. If you do that in round, you get negative 1.14. Then we're going to do the same thing for the one that's larger, 206.3 minus 206 divided by 2.5, the variance, over the square root of 90. Work that out, and you get positive 1.14. That's no coincidence. We want the exact same amount below and above, so that's why one is negative and one is positive, and they're the same number. Okay? And so if you look those values up in the table, the positive one is going to give you an area of 0.8729. The negative one is going to give you an area of 0.1271. So if we want the area between the two, we have to say the one furthest to the right minus the one furthest to the left. That will give us the area between the two. So if we say 0.8729 minus 0.1271, then you'll get 0.7458, and that's your answer. That's the probability that if 90 are chosen, that we would have them within 0.3 inches. Number 7 says Thompson & Thompson is a steel bolts manufacturing company. Their current steel bolts have a mean diameter of 139 millimeters and a variance of 64. If a random sample of 41 steel bolts is selected, what is the probability that the sample mean would differ from the population mean by more than 1.2 millimeters. So what's the chance that that sample mean would differ by more than, that's important too, more than 2.1. So it could be 2.1 larger than 2.1 millimeters bigger, or it could be smaller than or less than 2.1 millimeters smaller. So it's kind of confusing. Would differ by more than 2.1. Alright. So if you need to, maybe read that problem a couple times, because again, it is kind of confusing. But x bar we're given, and that's mu again, sorry. Mu we're given as 139. We're given a variance of 64. I know we need standard deviation eventually, that's 8. The sample size was 41, and it's very important that we had more than 2.1. Okay, this isn't greater than, this is more than. So if the average is 139, if we add 2.1 to that, then we want to know stuff bigger than that number, greater than that number. And if we subtract 2.1 from that, we want to know stuff less than that number. So it's kind of like this. We're going to figure out some z-score over here, because the smaller one is going to have a negative z-score. And we want to know all the stuff less than. And then we're going to figure out some other z-score over here. The one we add 2.1, we'll get a positive z-score. And we want to know the stuff greater than that. So to vary, and vary may not be the right word to use, to be different more than 2.1 millimeters means to be larger than 2.1 or bigger, in the bigger direction and in the smaller direction. Okay, so we need to do the same. We need to say mu minus 2.1, so that's 139 minus 2.1, or 136.9, and we need to say mu plus 2.1, so that's going to be 139 plus 2.1, or 141.1. Alright, so to find our z-scores, central limit theorem again, the sample's 41, the standard deviation is 8, so I have 136.9 minus 139 over, this will be 8 over the square root of 41. Okay, work that out in your calculator and you should get negative 1.68. Alright, and so we're going to do the same thing for this other number, 141.1. I bet you can guess what our z-score is going to be. Remember that pattern? Because we're going the same value above and below the mean. But I'm going to work it out anyway. Well, instead of a negative 1.68, it's a positive 1.68. Alright, so we have to be careful how we get these answers though. Because remember, if we want the area to the right, we have to say 1 minus. So if I want this area, I have to say 1 minus what I get from the table. If I want the area to the left, well, that's the way the tables are set up. They're set up to give us area cumulative from left to right. So we'll take the value from the table for negative 1.68. We'll have to say 1 minus the value for the table for 1.68. Okay, I've already looked this value up, and if you look this up in the negative z-score chart, you'll get 0.0465. So if you don't believe me, pause the video and look that up for yourself. You take that. Alright. Now, guess what the area is going to be to the right of this? You might could even guess it, because this is very symmetrical, what we're doing here. We're going to say 1 minus the area given in the table for 1.68, and that the value given in the table for 1.68 is 0.9535. So if I say 1 minus that, guess what I get? 0.0465. So it's the same area to the left and the same area to the right, and we want to add them together to get the probability. Okay, so you say 0.0465 plus 0.0465, and you'll get 0.0930. That's your answer. All right, number 8. The opera theater manager calculates that 11% of the opera tickets for tonight's show have been sold. If the manager is correct, what is the probability that the proportion of tickets sold in a sample of 703 tickets would be less than 13%? Read that a couple of times. To me, it's kind of amazing that we can even figure this out. The probability that if we sell 703 tickets, that the proportion would be less than 13% sold. So that's very interesting to me. So let's see. We now have to use a new formula. What we have in our denominator now for our z is not our sigma sub x bar, because we weren't given a mean. Do you notice that on that problem? We were given a percentage. A percentage is a proportion, all right, or a point estimate or something like that. So now, instead of a sigma sub x bar, we have something new down there. It's a sigma sub p hat that we need. Our formula, though, is sigma sub p hat squared. So whatever we get, we'll have to take the square root of that to get the bottom part, or the denominator, of our z-score formula. Okay, so we figure out this value by using the formula p times 1 minus p all over n. Okay, we were given in the problem that p is 0.11, or 11%. What is 1 minus p? You simply say 1 minus 0.11. Alright, so we have 0.11 times 1 minus 0.11 over n. Said, what if we sold 703 tickets? Okay. So whatever we get here, remember, is squared, so we have to take the square root of it before we even put it in the denominator of our z-score formula. Alright, so we get 0.0001396. If you take the square root of that, you're going to get 0.0118086. Okay. Now we want to know the probability that we would have less than 0.13, or 13% of those sold. All right. Now the formula that we have to use, we don't have means now. We don't have mu's and x bars or anything like that. We have p's and p hats, so our point estimates. So we want to know the probability that z is less than, And you could go ahead and work out your z. That's what we've been doing. And so it's going to be p hat minus p over sigma sub p hat, which for us on this problem is going to be 0.13, so this is from the sample, minus 0.11, this is the population proportion, divided by that sigma sub p hat, 0.011800086. When you do that and round that to 2 decimal places, you get 1.69. So I want to know the probability that z is less than 1.69. Remember, the less than was actually in my problem, so you can go back and look at that if you need to. Alright, so what we need to do is look that value up in the table. Less than, we take the value from the table. When you do that, you're going to get 0.9545. That's your answer. Number 9, suppose 56% of the children in a school are girls. If a sample of 428 children is selected, what is the probability that the sample proportion of girls will be greater than 50%? Okay, greater than 50%. So that's a pretty big deal. Okay. So greater than. All right. So we're given P equals 0.56. We're given that what if we took a sample of 428, and from that sample we got something greater than 0.5 or 50%, greater than 50%. All right. So our sigma sub p hat squared formula is p times 1 minus p over n. So divide that out and take the square root of that, and you'll get 0.023993768. So that's the denominator of my z on this problem. So z equals, we're going to have p hat minus p, so 0.5 minus 0.56 over 0.023993768. Divide that out and round to 2 digits, and you should get negative 2.50. So we want to know the probability that we get something less, greater than negative 2.50. Okay, so that means we need to look up negative 2.50 in our z-score chart. Now, since it's greater than, we want to say 1 minus whatever answer we get. When you look that up in the z-score chart, you'll get 0.0062. So 1 minus 0.0062. That's 0.9938. So what does that mean? That means that if you're told that there are 56% more girls in a school, and you take a random selection of 428, the probability that there'll be greater than 50% of those being girls is 99.38%, or 0.9938. Okay. Number 10. Suppose 57% of politicians are lawyers. Lots of them are. If a random sample of size 564 is selected, what is the probability that the proportion of the sampled politicians who are lawyers will be less than 51%? Round your answer to 4 decimal places. All right, it was less than, right? less than. So we were told the proportion is 0.57. Our p hat was 0.51. So we need to calculate sigma sub p hat squared. Our formula is p times 1 minus p, so that's 0.57 times 1 minus 0.57 divided by n. I didn't write down n. N was 564. So that's how many were chosen in a sample. Alright, again, if you divide all that out and take the square root of it, you'll get sigma sub p hat equal to 0.020846449. Alright, so we want to know, let's see, what is our z-score? Our z is equal to p hat minus p, so 0.51 minus 0.56 divided by 0.020846449. Work that out around the 2 decimal places and you'll get about negative 2.88. So was this problem less than or greater than? Remember, it was less than. So we just take the value from the table. It can be a really small value. And if you take the value from the table, you get 0.0020. Problem number 11. I believe this is starting chapter 10. That was chapter 9 problems. These are chapter 10. A market research company desires to know the mean consumption of milk per week among people over age 45. A sample of 306 people over age 45 was drawn and the mean milk consumption was 3.9 liters. Assume that the population standard deviation is known to be 0.7 liters. Construct the 98% confidence interval for the mean consumption of milk among people over age 45. Round your answer to 1 decimal place. Alright, we're given a lot of information here. Alright, we have n equals 306. We have x bar equals 3.9. We have sigma equals 0.7. We want to construct a 98% confidence interval. So that would be 98% confident that the actual value lies within the interval that we figure out. Okay, the formula that we use to do that is x bar, which we already have, plus or minus z sub alpha over 2. This is our critical z value, times the standard deviation over the square root of n. Okay, now if you look at table 10.4.1 on page I think it's 433 of your ebook, it gives you some of the basic critical z values that are used a lot. It just so happens that 98% is not in that table. So the way that we find that critical value is by figuring out alpha first. Alpha is, or 1 minus alpha has to be equal to 0.98. So this tells you what the alpha will be here in our z sub alpha over 2. Okay. So if you solve for alpha, you were to subtract 1 from both sides and divide both sides by -1, or you just guess and figure out, hey, that must be like 0.02. You could figure that out by looking at it probably. This is alpha. Well, notice that it's z sub alpha over 2. Well, what is 0.02 divided by 2? That's 0.01. So what that is, you know, if we were looking under the z-score chart, we have some little value here and here that would add up to be 0.01 as an area. Everything else in here would be 0.98. And then, of course, all of it added together would be 1. Well, if we could figure out this z-score right here, since area is cumulative left to right, you find the closest one you can. And you look at the area, not the z-score, the area, the closest area to 0.01 you can find. And that's going to be a z-score of 2.33. Okay, so probably need to pull that one up real quick. Tables. So if you look in the negative one, you're going to get a negative 2.33. If you look in the positive, you're going to get a positive 2.33. But I want to show you here, look. This right here, this is as close as you can get to 0.01. 0.0099. You know, that rounds up to 0.01. This one is 0.0102, but see, that's further away than 0.0099. So we use negative 2.33 as our critical value. Like I said, most of the common critical values were in that table on page 433, but we just had to figure out the one on this problem. So we have a z-score, a critical z-score of 2.33. So we say x bar, that's 3.9 plus or minus 2.33 times sigma divided by the square root of n. We were given standard deviation as 0.7 and n as 306. So work this out right here, and then we're going to add and subtract it from 309. So when you do that, you'll get I said 309, I meant 3.9. 3.9 plus or minus, I kept the decimal pretty exact, 0.093238064. That's as close as my calculator would get it. So that forms an interval here, and it doesn't matter how you write this. You can put these in either way that you want. But if you put the bigger number on the left, it would be 3.99. That's the larger. And 3.81 is the smaller. A lot of times we write the smaller one on the left, so you could write it like this. There's a lot of different ways to write these answers. It's even acceptable to write it as an interval, like this. So, but all these mean the same thing, okay? So the confidence interval is from 3.81 to 3.99. So we're 98% confident that the actual value will lie in that region. Okay. Number 12. The mean monthly water bill of 79 residents of a local apartment complex is $138. So that's the mean. What is the best point estimate for the mean monthly water bill of all residents of the local apartment complex? Well, given the information that we're given, we're told that the mean of 79 is 138. The 79 different residents, the mean of their water bill, man, that's crazy. 138. I would be going insane right now if that was my water bill. Maybe they all have pools or something. I don't know. We're not given anything else. So this is our best point estimate right here. So the answer to this one is 138. It's actually that easy. At a local college, a study found that students earned an average of 14.8 credit hours per semester. A sample of 94 students was taken. What is the best point estimate for the average number of college credits per semester for all students at the local college? Well, that's all we're given, 14.8. There's no way to calculate anything else. So that's the best point estimate we have. Okay, so the answer is 14.8. Need more questions like that. All right. Consider the value T. So this is T distribution, student T distribution. such that 0.025 of the area under the curve is to the right of t. Well, that's important, to the right of t. 0.025 to the right of t. 0.025 is pretty small. So let's look at these different charts. This one has something shaded to the right. This one has something shaded to the left. This one has something shaded to the left and the right. This one has something shaded in between, and that's not 0.025. That's a lot more. That's probably more like 0.975. Anyway, it's this one right here. I said I wasn't going to answer any, but it's to the right. I mean, this is the only one that has one t shaded to the right. Okay, that was step one. Step two. Assuming the degrees of freedom equals 4, select the t value from the table. Well, remember how to get degrees of freedom. It's n minus 1. So n does equal 5, but it tells us the degrees of freedom is 4. That is correct, if n equals 5. All right, so if degrees of freedom is 4 and the t is 0.025. So degrees of freedom is 4, the t is 0.025, then it's this answer right here, 2.776. That's our critical t value. I don't know why it doesn't say that anywhere, but that's our critical t value. Okay. Well, that was not very complicated. Number 15. Consider the value t such that 0.05 of the area under the curve is to the left of t. So I'm looking for an area of 0.05 to the left of t. This has something shaded to the right. This has something shaded to the left. This has something on both ends. This has something in the middle. So this is the only choice that you could even consider. And it's because it says left of t. Assuming degrees of freedom equals 30, select the t value from the table. Okay, so degrees of freedom equals 30. So scroll down. This table is also in the back of the book. It's probably on your formula sheet. It's the student t distribution. So here's 30, and we had a t of 0.05. All right, so the t of 0.05, we get this value here. Now, it's important that you don't enter in this answer right here. You see, it actually selected it. Look, there's a little plus or minus button right here. Since it was to the left, that's kind of like z-scores on the left side. They're negative. Well, t-scores on the left side are negative as well. So since it was to the left, you got to make that negative. So you've got to select this, and look what it put down there, negative 1.697. And that's because it was to the left. If you want to look back, remember it was on the left side. These are negative numbers on the left side, the t values. They're like z values, but they're t values. Okay. Number 16. All right, number 16 took me a while to work out because we actually have to go through and calculate some of the things that we learned in the first couple of chapters. Maybe they're around chapter 3 and 4, even before then, because the first thing we do is have to calculate the sample mean. Okay, so read through the problem here. You're given 4 values. So at least the stuff we're calculating, we only have 4 numbers to do that. Okay. It says we want to construct a 90% confidence interval. We're also told the population is approximately normal. So we need to know that. All right, so we have an n equals 4. So degrees of freedom equals 3. We'll probably need that somewhere. Alpha is 0.1. That's important because when you say t sub alpha over 2, Our critical t-value is t sub alpha over 2. A 90% confidence level or interval. We say 1 minus alpha equals 0.9. So that means alpha is going to be 0.1. T sub alpha over 2, or the critical t-value, is t sub 0.1 divided by 2. So that's t sub 0.05. So when we use the chart to find our critical value, that's the column we have to go to. Alright, again, it took me a little while. There is a formula on your sheet for sample standard deviation. Remember what you have to do. You have to have a column, and you have to figure out the mean, and then you want to say x minus the mean. These are deviations, and you want to square them, and then you want to sum all those up, and then we divide by n minus 1. Okay, so I went through this problem a couple times to check all my calculations, and I got, once I worked all this out for our problem, I got a mean. Let's see, what was my mean? In case we need that again. I think we actually have to enter that in step 1. I got a mean, sample mean of 99.375. You get that when you add them all together and divide by 4, because there were 4 values. I think it says around the 2 places, so that's 99.38. Now when I actually do all my calculations for this, I don't use this rounded answer. I use this answer because this is actually an exact answer. Okay, the calculator stops at point, at the 5, so it's an exact answer, and that's what I use. So then I calculate the sample standard deviation, and I get this long decimal, 10.61677132. Any calculations that I use with the standard deviation, I'm going to plug that long number in. Though I believe in step 2 you do have to plug in the standard deviation and ask you to round the 2 places. It's 10.62. Okay, now remember I told you degrees of freedom, we had 4 data items, minus 1 is 3, and so I told you whenever we find the critical t-value we need to use the column that has 0.05 in it. So you may be wondering, why do we need the critical t-value? Because it's part of our formula for the confidence interval. Hopefully you knew that. Hopefully you've read through the book and you saw that. Our formula for a t-distribution is x bar plus or minus t sub alpha over 2 times s over the square root of n. S is sample standard deviation. Of course, n is the sample size. That was 4. We have to figure this out. We figured out what column to use, so we have to go to the table and see it. Okay. This one said calculate the mean, calculate standard deviation, find the critical value. That's what I'm going to do now. You can bring up the tables, the t table, area in one tail. Okay. 0.05, remember that's what our t, it was t sub 0.05, and our degrees of freedom is 3. So you see our critical t-value, 2.353. That's our critical t-value. Alright, so this t sub 0.05, that's, I said 2.353. And here's our formula, x bar plus or minus t sub alpha over 2 times s divided by the square root of n. So that's going to be, remember our x bar, we figured out our mean. I like to keep things as exact as possible. So 99.375 plus or minus, got this product here of our critical t-value, that's 2.353 times 10.61677132, all divided by the square root of n, or the square root of 4. Alright, so work that out add and subtract it from 99.375, and you're going to get 86.89 and 111.87. So, of course, you get a lot more decimals than that, but yours should be pretty close, almost exactly on that. Okay? Lower endpoint, upper endpoint. So that's where you put in your two values. A research company desires to know the mean consumption of meat per week among males over age 23. They believe that the meat consumption has a mean of 3.8 pounds, they eat that much meat a night, and want to construct a 95% confidence interval with a maximum error of 0.1. So that's that maximum error of 0.1 pounds, that's like the error in our problem. Assuming a variance of 0.84 pounds, what is the minimum number of males over age 23 they must include in their sample? Okay, so this is one of the size requirement problems. This is problem number 17. We were given mu equals 3.8. We were given variance equals 0.64. We want to know the size. The size, the formula that we use is z sub alpha over 2 times sigma over the error squared. Okay, that'll give us the sample size that we'll need. So the formula is pretty easy. You can see it doesn't require a lot of stuff. I mean, this is all we have to do for sample size. We're given standard deviation, we're given variance, so we can figure out, we're given mean, we're given variance, so we can figure out standard deviation, take the square root of 0.64. Okay. For there to be a critical z-score, there had to be a confidence interval, 95% confidence interval. Okay. So that is a z sub alpha over 2, where alpha is going to be 0.05. But I believe your book will list some of those critical z values. We use 95% a lot, not exclusively, but a lot. The critical z value for 95% is 1.96. Okay, so that's what we're going to plug in our formula. And before you say, what about negative 1.96, we're going to square it so it doesn't matter if it's positive or negative. So n equals 1.96 times the standard deviation is 0.64 over the error. The error was, I didn't write down the error. The error was 0.1. Remember, it said within 0.1 in the problem. And so, believe it or not, it's that easy. You say this number times this number divided by this number and square it. And you're going to get out some decimal, but round it up. Okay, so that's going to be 246. That's your answer. An economist wants to estimate the mean per capita income for a major city in Texas. He believes that the mean income is $21 and the standard deviation is $10.9. How large of the sample would be required, and this says in thousands of dollars, so how large would a sample be required to estimate the mean per capita income at the 95% confidence with an error of almost 0.56? Okay. So the error, I did remember that this time, 0.56. We were given that the mean given was 21. We don't even need that. We were given also a standard deviation this time. That's good. 10.9, 95% confidence level. So that means that your z sub alpha over 2, your critical z value, is still 1.96. So n is equal to 1.96 times sigma, your standard deviation, divided by your error, 0.56, squared. Work that out in your calculator. You should get 1455.4225, which if you round up, that's 1456. Problem number 19. The State Commission wants to estimate the fraction of 10th grade students that have reading skills at or below the 8th grade level. In an earlier study, the population proportion was estimated to be 0.23. How large a sample would be required in order to estimate the fraction of 10th graders reading at or below the 8th grade level at the 95% confidence level with an error of at most 0.03? Round your answer up to the next integer. Okay? So notice we didn't have means in here, we had proportions. We were given a population proportion. So that's important because we have a different formula if it's proportions than we do than if we have a mean given. So if we have a proportion given, p hat was 0.23. The 95% confidence level tells us that our z, critical z, is still going to be 1.96 because of the 95% confidence interval, or level, sorry. Our new formula is critical z squared times p hat, the point estimate, times 1 minus p hat, all over the error squared. I believe our error, maximum error we want in the problem, was 0.03. So we're just going to plug and chug numbers. 1.96 squared. P hat was 0.23. 1 minus p hat would be 1 minus 0.23. And that's all over the error squared. So be careful when you work that out in your calculators. Follow your order of operations, and you should get 755.9415111. Round that up to the next nearest integer, and you get 756. All right. So now last problem, number 20. 2 steps. First step's easy. Second step is a little more complicated. Let's see though. Suppose a sample of 822 new car buyers is drawn. Of those sampled, 205 prefer foreign over domestic cars. Using the data estimate of the proportion of the new car buyers who prefer foreign cars, enter your answer as a fraction or a decimal rounded to 3 decimal places. So we want to know the proportion of new car buyers who prefer foreign cars. So it's 205 divided by 822. That's all the data we have to go on. 205 divided by, so it's 205 out of 822. Okay, if we do that, we get this long decimal. It does tell us to round to 3 places. I'm going to write it out because I think we have to use it somewhere else. If we round to 3 places, that's 0.249. Okay, so that's our point estimate. And then it says, it adds a little bit, using the data, construct the 95% confidence interval for the population proportion of new car buyers who prefer foreign cars over domestic cars. Round your answer to 3 decimal places. All right. Remember, our confidence interval, we're going to need a critical z-score. We had a 95% confidence interval. With proportions, we're going to need a sigma sub p hat, and that is the square root of p hat times 1 minus p hat all over n. This is straight out of your book. P hat times 1 minus p hat all over n, and take the square root of that. So when you do that, you get 0.015082861. Alright, and so we're going to use p hat plus or minus sigma sub p hat times our critical value z sub alpha over 2. Your book may have that written first, but it's either way it means the same thing since you're multiplying. Okay, and from that we can form our confidence interval. So remember, p hat was 0.249 something. That's going to be plus or minus 0.015082861 times 1.96. Again, it's a 95% confidence interval, so that gives us a critical z value of 1.96. Work that out, and when you do that, you're going to get 0.219 as your smaller answer. So it'll be greater than that. And you're going to get 0.279 as your larger answer. Okay, hopefully that helped. I would suggest working through the review maybe once by yourself, and then after that, if you have any questions, please email them to me, and good luck on your test this weekend.